Okay, we made some good progress through discussion in class regarding the problem of the water flowing out of the cylinder. And the way this problem is that you're discussing is stated, you have a certain horizontal range of the water stream after it leaves the tube and the vertical distance that it falls. Y is going to stand for the distance of the water surface above the outflow hole, above the point at which the flow ceases. We have the cross-sectional area of the cylinder, A, CYL, cross-sectional area of the hole, A, exit. Didn't want to call that A hole for reasons that might be obvious. Then our ultimate goal is, well, there's several, but ultimately we want to see how dy dt is related to y, because this is actually going to give us a differential equation that's very easy to solve. Okay, you solve it with just knowledge of first semester calculus. In this case, we can determine the ideal exit velocity. That's the exit velocity we would have if there were no non-conservative forces. The ideal situation, no viscosity, no drag between the water and the walls of the tube. And that means our work done by non-conservative forces would be zero, so that the change of potential energy plus change in kinetic energy is zero. So we can derive an ideal exit velocity here and also gain a lot of insight into the work energy theorem. But we have two other ways of approaching this. First of all, we could observe our V exit. Well, we actually can't directly observe this velocity in any simple way, but from the horizontal range of the water stream, we can figure out what the velocity of exit is. That's just a simple projectile problem. Everybody understands that, I believe. And also we could get it from dy dt, assuming we know the cross-sectional area of the exit tube, and we do. I haven't told you what it is, but it's a standard piece of tubing. And the cross-sectional area of the cylinder, which we assume to be uniform. Now, the way I've drawn the cylinder, it looks a little irregular, but actually this model makes a pretty uniform cylinder. Not perfectly, and we could maybe even try to measure how imperfect that is. But for right now, this is what we have. So there are three ways of determining an exit velocity. From the horizontal range, from dy dt, and of course dy dt means that we can graph y versus t. Okay, we get a graph, and we can make a good estimate of dy dt based on a smooth curve fitting our data points. And also we can get our ideal V exit based on conservation of energy. We compare all three, but especially the comparison of the actual V exit with V exit from our data indicates, I'll call it friction loss. And that's actually associated with what we're going to call pressure loss, and we'll worry about that a little bit later. Now there's more we want to say about this, but this is the task for right now. Now, I've added a little bit of data here. At the top mark, the horizontal range appears to be about 50 centimeters. I didn't get to observe that for the second mark. I kind of think it was maybe around 40, but I don't want to say any more than that. The third mark was 24 centimeters. The fourth mark was 18 centimeters. So you know what your marks are, 138 centimeters. This is about 80. This is about 40. This is about 20. And I said centimeters, it's millimeters. 138 millimeters, 80 millimeters, 40 millimeters, 20 millimeters. I think one of these had a 3. I think maybe the 40 was a 43. I don't remember. Maybe the 80 was an 83. But you have your data, so you know. So that's where we are. Now, again, ultimately, we would like to get this for the ideal case and for the actual case.